This is Dr. Ron Kern, and I want to go over a little bit of our nuclear chemistry, the part that you're going to need for here in the exam for our waves and nuclear energy portion of the course. We're not getting into this very in big depth. I want to present a few concepts and then also go into maybe some sample problems that would help you prepare for what you're expected to know on the exam. This will be covered in depth in physics. I taught physics for quite a few years, and it's an interesting area to get into in physics. And in chemistry, it's interesting, but it's not going to be critical to us understanding the future chemical processes we're going to talk about. But at least it's going to give you some theoretical background about isotopes and the development and the production of energy. You see in the production of nuclear devices, of course, militaries around the world can create two nuclear devices. One is a fission bomb. That's one of the earlier bombs. And then you can have a fusion bomb, the thermonuclear bombs that we have today, the very large, powerful bombs, where you fuse atoms together. So let's look at here. Usually, you're going to have a large nucleus, uranium, plutonium, something large like that. It's going to have a neutron come in and split it into two daughter elements, smaller daughter elements. It's going to release more neutrons. That's how you get a chain reaction. As one neutron splits an atom, you end up getting two or more daughter neutrons being produced. That's going to split multiple atoms later, and each of those produce multiple neutrons, and you get a chain reaction, and you get a thermonuclear explosion, and the release of a huge amount of energy. So let's look here at that. All right, so here we are. We've got fission here. I've got uranium-235, and if you look on the periodic table, you can see normally the average isotope of uranium is 238, but in this case, we're looking at an isotope 235, one that's very fissionable and is used for nuclear material. I've got a neutron coming in. You see the neutron with the arrow there. It's going to split and break the uranium atom into two parts. In this case, it's going to be krypton and barium. It could be two others, and we'll have an example where it's two other possible daughters elements. But in this case, I've got barium, which has an atomic mass of 141, krypton with an atomic mass of 92. And the question is, do those add up to 235? No. And the thing is, should it add up to 235? The answer is no. Let's actually look and let's go through step by step, and I'm going to show you that the amount of atomic mass units into the process is equal to the atomic mass units that came out of the process. All right, so look at the uranium-235. So it has 235 mass units. So I'm going to put up here 235. And you notice that I had a neutron come into it. Well, neutrons are like protons. They have an atomic mass unit of 1. So the amount of atomic mass units going into this process is actually 236 atomic mass units going in. Well, let's see what's produced. Barium with atomic mass units of 141. I've got plus krypton. Krypton with atomic mass units of 92. And note that I have 3 neutrons being produced. So does 141 plus 92 plus 3 equal 236? And the answer is yes, it does. So you have to count the neutrons coming in, the neutrons going out as part of those products and byproducts, the inputs and the outputs. So you'll see here that 236 atomic mass units in, 236 atomic mass units out. Okay, let's check out fission a second. Now, we're not going to dwell on fission. those are not processes that occur in nature. We get spontaneous radioactive decay in nature, and the splitting of atoms can happen. But the fusion of hydrogen atoms, you see two isotopes of hydrogen here, because hydrogen is normally just a proton and an electron. But look at this deuterium. You see a proton and neutron. We're used to a proton and electron. There's no neutrons in hydrogen. There is in this because it's an isotope of hydrogen. It's called deuterium. And look at tritium down there. It's a proton and two neutrons. Well, those unstable isotopes of hydrogen can be fused. Of course, it still takes a thermonuclear device to do it. It also happens in the inside of stars. But so that's why it's not normally done on Earth, except because man has determined the process to do that. And of course, it does take place inside stars. And what happens, it creates helium plus energy. And that's all I want to say about that. Let's look at types of radioactive decay. You can hear about alpha particles, beta particles, and gamma particles. If you hear about an alpha particle, it is the most ionizing of the atomic decay products. It's easy to stop. It's stopped by paper and clothes and stuff. It's not very penetrating, but if it gets inside your body, it is very ionizing and is considered the most deadly of the radioactive decay products. And what is it? A helium nucleus. 2 protons, 2 neutrons, no electrons. So what's its valence? +2. It's got 2 protons in the nucleus, so got 2 positive charges, 0 negative charges, so it's got a valence of +2. And when it gets in your body, of course, it wants to get those electrons, and it destroys cells, and it's very damaging to your body as it tries to become stable. The other one is a beta decay. Beta decay gives off an electron. So if we say, what's a beta particle? It's an electron. We'll look at that in more detail because the releasing of that electron actually isn't an electron that was already there. It's going to be an electron that's produced from the mutation of a neutron. It's actually going to be a neutron that mutates into a proton and electron, and it releases that electron. Of course, when that neutron becomes a proton, that element changes. That element has more protons. It's no longer that original element. That's why the byproduct of uranium, atomic number 92, in that process, one of the byproducts is plutonium, atomic number 94. Well, how did it gain 2 protons? Well, 2 neutrons mutated into protons and released 2 electrons on the way. So 2 beta particles were released in changing those 2 neutrons to 2 protons. And the third is, just because we have these huge molecules, plutonium is a great example. Those electrons in those outer shells like that, we've learned earlier, are higher energy. We talk about the electrons absorbing energy, heat. We did that in the flame test. The electrons jumped up to higher energy levels, and when they dropped back, they released a photon. Blue light, green light, orange light. We saw them as those colors. In this case, they have those outer electrons are at such high energies that the photon that's released happens to be a gamma ray. And of course, we just learned in waves, what is the highest energy wave on the electromagnetic spectrum? Gamma rays. So you can see they're incredibly high energy waves that these photons that are released, they end up being gamma rays in these large elements like uranium and plutonium. All right, let's move on. So what's alpha decay? That's where when the nucleus emits a helium nucleus. Remember, it's a nucleus. It's He2+. It's got a valence of +2 because it has no electrons being produced. Gamma production. Let's look at it. All right, here you see in beta decay, you see a carbon being mutated to a nitrogen. What happened? A neutron converted to a proton, so it's no longer carbon. Carbon has 6 protons, not 7. It now becomes a nitrogen atom, and of course that neutron, in creating a proton, also releases an electron, and that is the beta decay. I've circled it there. That's that electron being released, is the electron being produced by the transmutation of a neutron to a proton and an electron. And then you have a large, here shows you a plutonium atom, just those excited outer electrons falling to their ground state releases gamma radiation. Very, very, very high energy photons. All right, let's look at the problems that we are interested in doing here. Here is an example. Okay, let's follow through and let me show you exactly how to solve something like this. A plutonium atom was bombarded with a neutron. Fission resulted. One of the daughter products was barium with an total atomic mass of 148 atomic mass units. It also created 4 neutrons and then another daughter element. The question is, can you determine that daughter element? We'll do exactly what we did last time. We have to know the total atomic mass units going into the process, and if they're going to equal the total atomic mass units coming out of the process. So, go to your periodic table. Let's look at plutonium. And if I write, let me put plutonium down here. And plutonium, of course, is element that's got 94 protons. And it has an atomic mass. Look at the atomic mass on your periodic table. You're going to see its atomic mass is 244 units. That's going to be the average of its isotopes. And then, of course, we added a neutron in, so there's another atomic mass unit. So 244 plus that one atomic mass unit means I'm starting off with 245 atomic mass units. And at the end, I'm going to have 245. Well, I see where 148 of them are, and I see where 4 of them are, because I have 4 atomic mass units creating the 4 neutrons, 148 creating the barium. So 148 plus 4 is 152 I've got accounted for. All I have to do is subtract 152 from that, and I end up with 93 atomic mass units. So I know the element that I'm going to create is going to have a total mass of 93. Well, how many protons are left? 94 minus 56. So 94 minus 56 is, that number is 38. And I look at the periodic table, and I see that that is strontium. So 56 plus 38 equals our 94 protons. And 93 plus 4 plus 148 equals our total mass of 245 atomic mass units. All right. Put that there. And then what I'm going to do is I'm going to bring up one for you to solve. Pause the video, go to your periodic table, and see if you can use this process to solve this problem. A thorium atom was bombarded with a neutron. Fission resulted. It came out with yttrium, 3 neutrons, and what other daughter element? Welcome back. Did you solve it? Were you able to look at your periodic table and come up with the inputs and outputs so that you have the total atomic mass units going in equals the total atomic mass units going out? Let's check. Check your work with this and see how you did. Thorium. I'm going go to the periodic table, and I'm going to find thorium here. And I'm going to see that it has an atomic number of 90. Thorium has an atomic number of 90 protons. And I'm looking at its atomic mass. The atomic mass of thorium is 232 units, atomic mass units. So 232. All right, I added a neutron. It was bombarded with a neutron. So what was my inputs? I had 233 that I must account for. Well, what do I have then left? Well, first, let's see what element we're talking about. I'm going to take, thorium has 90 protons, but I'm using up 39 of the protons for yttrium. So how many protons are left? So I can find what element on the periodic table it is. Did you come up with the number 51? It's got 51 protons left. And what is that? That's Sb, which is the symbol for antimony. So, or antimony, however you want to pronounce that. So antimony here has 51 protons, and 51 plus 39 is going to give my 90 protons. How many? What is going to be the atomic mass of antimony, that isotope of antimony? You can't look at the periodic table. You're going to have starting with 92 in yttrium, plus 3 neutrons, that's 95. And if I subtract 95 from 233, that'll tell me what the atomic mass of my antimony is. So what do I have here? 8. I have 138 atomic mass units. So I'm going to have antimony with 51 protons and a total atomic mass of 138 atomic mass units. And then does that add up? Does 92 plus 3 plus 138 add up to 233? If it does, you would have the correct answer. Do the 51 plus the 39 protons add up to the 90 protons that we started with in thorium? I hope this helps, and you feel prepared that you could solve problems like this, and that you have a little basic understanding of nuclear chemistry.